Good afternoon, everyone. Thanks for joining today's webinar, Improving Traffic Flow in Real Time with Siemens Scoot. My name is Connor, and I will be your moderator. Before we get going here, just a few housekeeping things wanted to run through really quickly. Just so everyone knows, all phone lines are muted, so if you have any questions, please use the chat feature within your GoToWebinar toolbar. Presentation will last about 45 minutes or so, which will give us some time to answer any questions you may have at the end. And by attending today's webinar, you are eligible to earn TARP points through IMSA. For those of you who provided your IMSA number during the registration process, Western Systems will go ahead and handle that submission process for you. And if you'd like a copy of today's slides, they are available for download within the GoToWebinar toolbar. And lastly, today's presentation will be made available on demand. You'll get an email tomorrow with a link to view it. All right, with the housekeeping out of the way, I'm excited to introduce today's presenter, Kai Antrim, Territory Manager at Western Systems, and Zach Hoyting, Sales Manager at Western Systems. Guys, the floor is yours.
All right, thank you, Connor. Thank you, everybody, for tapping in again. Hope you all are staying safe and keeping busy out there. It's interesting. When we first started doing these, we weren't really sure what to expect. You know, I mean, we're such a relationship-driven industry that it's important to have these face-to-face meetings. So definitely an adjustment period for all of us. You know, me and my cohorts were used to going out and being out on the street and in the signal shops and at City Hall, meeting with people, you know, having face-to-face conversations. But this has been an okay way to kind of tide us over. And so we appreciate you guys kind of all tapping in for these. Over the next 3 or 4 weeks, we've pretty much got a full lineup of, we're kind of working off this Tuesday and Thursday schedule. It's a way to connect with you guys while at the same time an opportunity for you guys to keep up on your TARP points. We've kind of come up with a special arrangement with IMSA to be submitting these during this time. They were really supportive of that. So definitely tell your other coworkers and people who might be IMSA members that this is a good opportunity for them. So today we're going to talk about Scoot, adaptive signal operation and powering the future of mobility. For those of you, I think most of you have some familiarity with Western Systems, but we're headquartered in Everett, Washington. We were founded in 2001. We primarily used to build traffic signal cabinets for kind of the state of Washington, but we've now moved to encompass everything you might find out at the street. So signal poles, enclosures, controllers, controller cabinets, anything that you might need within your traffic department. One of the things today that seems to be growing in popularity is the need to make our city smarter. So from a smarter city perspective, Western Systems carries a broad line of products that handle mobility needs all the way, like I said, from hardware up to all the software, basic software for more simple systems, all the way up to enterprise level systems such as Scoot. So without further ado, I'll jump into our adaptive signal system that we offer through Siemens called Scoot. Scoot is a Siemens product that is deployed heavily all over the country. This is a map that shows on the left side shows our deployments. We sell Siemens products, including Scoot, in Washington, Oregon, Idaho, Montana, and California. So we've got a number of deployments right here in your backyard. If you guys are interested in hearing from agencies that have deployments of Scoot, we'd be happy to put you in touch with the right people. Scoot stands for Split Cycle Optimization. Scoot Split Cycle Offset Optimization Technique. Say that 10 times really fast. I can't even say it once, but essentially what it does is it's got 3 optimizers: the split, the cycle, and the offset. And we'll get into that a little bit today.
Right.
Scoot is a real-time.
So, yeah.
Oh,
go ahead.
My bad. Go
ahead. We practiced so many times and we still can't get it right. So we're kind of doing this duo format just to kind of keep it a little more interactive and maybe give Kai's voice a break because he's been doing a lot of these webinars. So for all those that don't know me, my name is Zach Hoyting, sales manager here at Western Systems. So I've been a part of a lot of these Scoot installs. So I'm gonna just give a little piece of information and my know-how about the technology and how it can be useful out there in the street. But you know, the big question is, what is Scoot? You know, those that aren't familiar with it, it's a real-time adaptive control system, and we'll get into the nuts and bolts of what makes it a real-time system. But Kai kind of hit on that as far as the splits, cycle, and offsets, and those optimizers. But the main purpose of Scoot and the traffic model behind it is to predict the congestion states on the transportation network, meaning your intersections, right? So the purpose is to improve that network every second, 24/7, 365, right? And so there's three different pieces that are part of the Scoot traffic model, and that's utilizing historical, but also the current information that's entering the network. And that's, you know, that density and flow as those vehicles are approaching or leaving the intersection and moving on to the next one. So the final objective is obviously to better optimize the traffic infrastructure, such as the traffic lights, right? And then we're also, the other optimizers that we're looking at is the pedestrians and bicyclists and the transit signal priority and, you know, emergency vehicles. Those are all parts of the adaptive portion, and Scoot looking at all those different pieces and parts. So, you know, in short, kind of how it's doing that, it's utilizing detectors that are out there. Those are the eyes and the ears of any adaptive, and more specifically Scoot. We're using those to monitor continuously and take that data and make real-time decisions as vehicles are actually approaching the stop bar. So we'll add or decrease time, and we'll get a little bit more into that here in the next coming slides. And then what it also allows us to understand is what the cues are. You know, what are the appropriate calculations so that we can adjust that cycle or those splits and offsets. And this is all done second by second. We're continuously making those adjustments and changes. So if we actually had a live map up there with Scoot, you'd actually see it, and you'd see that cycle timer and the splits being adjusted. And then if we were looking at intersections simultaneously, we maybe see some adjustments of the offsets every cycle. So those things are what makes Scoot and makes it so powerful, is being able to take that data and really quickly make measurements and then push it down to the field so that we're easing that burden or that saturation during whatever cause or effect it may be. So the real question I have for a lot of people, you know, is would you prefer a proactive or reactive adaptive technology? You know, now if I was able to take a survey of everyone or hear everyone's opinions now, I mean, I understand we're all muted, but I think the consensus, I know the consensus would be proactive, right? We want, as cars are approaching, that we can add time or take away where maybe not necessary or needed. And so what is Scoot that makes that important, and how does it do that, right? So what we're doing is using that model that's built up in the front end of Scoot, and we're being able to measure all the things being cues, how long it takes people to get off the stop bar, what's the speeds they're going on, and we're inputting all that data into Scoot. So then that way we watch and see how it acts when we put that data point into the system. And then what it's doing is it's understanding over time how many cars are coming and going from the intersections or that corridor or that grid network that's out there in your agency. So and then what it's always doing constantly is changing the splits. So those are recalculating at every approach. So we're always adding and taking away depending on the demand that's at the intersections. Then once per cycle, we're able to adjust the offsets. So based on that platoon where we're trying to capture as much or as many vehicles on that corridor, it's going to adjust that so that we are timing that out appropriately. So as the cars are approaching the next intersection, the goal is obviously to make them hit the green and then alleviate and get as many cars through each intersection. And then what we can do with the cycle time is that we can actually adjust the cycle time. That can be on a single intersection or a region of intersections, and that's the typical methodologies. We create regions within a network under Scoot, and those can be changed as quick as 2.5 minutes or up to 5 minutes at the earliest is typical. Of course, if no adjustments are needed based on the demand out there in the intersections, the cycle time will remain the same, and we'll continue business as usual. The nice thing with Scoot as well is how we make it a real-time system and proactive is it does not require any plan. So what we utilize literally out of the box is what you guys have as your min times and things of that nature. And then what Scoot is going to do is never going to break those, but it's going to build off those and change based off each approach that each intersection seen with the demand of vehicles.
So we're going to talk a little bit about some of the benefits of utilizing Scoot. Scoot has its own internal algorithm that maximizes the use of available capacity by keeping traffic moving. It's also got a saturation mode, which continues to optimize signal timing even when saturated. It helps to reduce the duration of the saturation period. One of the big things we want to talk about is the variability of travel time. You know, people aren't nearly as concerned if they've got an hour-long commute every single day and it's predictable. It's when that becomes unpredictable and you've got 40 minutes one day, an hour and a half the next day. So one of the things that Scoot really helps do is make your travel time more reliable, more predictable. It's going to stop and delay, stops and delays to reduce your overall travel time. The algorithm is able to adapt to rapidly changing conditions. So for event management, you know, if there's unexpected type events, Scoot is, you know, always running in the background and able to make those changes on the fly. Of course, improving safety. Scoot's primary goal is optimization of the offset. So that reduces overall delays, also reduces the number of stops and rear end collisions. So you think about, you can change the splits and you can change the cycles, but you really have to be looking downstream at the intersections down the way and making adjustments to the offset to ensure that you're not creating a situation where there could be rear end crashes. Support for bus rapid transit. So TSB and priority is definitely a hot button topic right now. So standard TSP operation such as Opticom, supported directly through the controller. Scoot also has the ability to run kind of a BRT advanced operation using a data feed from a transit system. So you've got your transit system that's already pumping data into that system. Scoot is able to digest that information and help move transit vehicles more efficiently. Some of the benefits of Scoot from a pedestrian perspective, the ability to deal with oversized PEDs. So as you guys know, a lot of pedestrians or groups of pedestrians are going to need a lot longer than the phase would otherwise allocate. That makes it easy to get out of step with all the other intersections. So oversized PEDs in Scoot helps make sure that PEDs get the time they need to cross the street without screwing up the entire rest of the system. Negative PEDs, you know, an example of a negative PED would be making sure a flashing yellow arrow is not coming on when there's a PED. So people are trying to slip between a couple cars to make a permissive left, and we don't want that to come up if there's a PED signal activated. Advanced pedestrians, the ability to start the PED timer before the right turn light can reduce PED collisions and fatalities by moving the pedestrian into the intersection before the vehicle. So variable PED timing, depending on the specific needs of PEDs, reducing the amount of time that the PED clearance is up if not needed, or the flip side of that, extended when it is necessary. A big deal is transition. A lot of efficiency is left in transition. You go into preemption and it takes an entire cycle to get back in step. Well, in Scoot, you don't have to have that transition period. So that's cutting out valuable time that can be used to be moving people safely through the intersection. So preemption, oversized PED timing, those aren't going to cause transition type events. Balanced saturation, we'll talk a little bit about split weighting and biasing and gating. Essentially, it's not too hard to move traffic efficiently down one corridor. You just give everybody a green light. But Scoot is looking at the overall system and how is that treating the side streets. And if we're getting backups on the side streets, but improving the main line, are we really accomplishing our overall goal? So in terms of biasing, making decisions based on how it's going to affect the entire system. We've got another slide on gating. I'll talk about that a little bit, but essentially you don't want to fix one problem just to create another one. School incident and event management, safety is a big concern, and having these events that come out kind of unexpected and create large flows of traffic, a standard traffic signal plan is not really ready to handle these unexpected events. So programming in Scoot gives you the ability to be prepared for those kinds of events. So benefits in summary, improved traffic flow. You can give you guys some of the use cases of people who've implemented Scoot, the reduction in travel time, the increase in reliability, the decrease in emissions, reduced congestion. Scoot is able to work within your whole ITS network, so managing the entire system. As I said, adapt to unexpected traffic conditions. There's no black box, so that essentially means we're not taking your controller and hijacking it. All it's doing is holds and emits, but you could still use whatever equipment you have out there in the field. Scoot is just essentially a modular system that can be added on top of just about any traffic control system that's already out there. Applications, so gating. I talked about this a little bit as one of the benefits of Scoot. So the idea here is you can push a green band down a corridor, but where are they going to end up? If they're going to end up, trying to get onto an on-ramp or getting around a corner or wherever it is, we don't want to create a situation where we pushed a bunch of traffic into a sensitive area and then backed it up in the intersection. That doesn't make any sense. So gating makes sure that your offsets, your splits, your cycles, and your offsets are in line with moving traffic as the other streets are able to handle it. So we don't want a position where we've moved everybody through a couple intersections, but then we've backed up future intersections a long ways away. So like I said, an example of that is like on a freeway on-ramp. If our goal is to flush people from a corridor onto I-5, but then we've just completely crowded the on-ramp, that's not going to be very helpful to our overall goals.
Kyle, let me add to that a little bit. Yeah.
Go ahead.
The idea behind the gating is, on-ramps isn't a perfect situation, and gating and being a good solution for that is that when you typically have an on-ramp that's, jammed up and there's nowhere to go, ultimately cars start entering intersections, and then those intersections are jammed up, so no side street traffic can move. So what Scoot can do is it can measure that on-ramp and understand where the queue is and if there is any capacity or not. So ultimately what we can do is hold back the traffic from entering into that on-ramp, and then Scoot will adjust and really work on the side streets until that capacity is relieved or there's capacity on that on-ramp, and let the cars come through, and then it'll go back to that same operation until that on-ramp has cleared itself for a time being. So gating is really a powerful tool when it's coming to these areas where they're alongside a freeway and people are trying to exit or even enter into a city network.
Thank you, Zach. CAST. So as Zach mentioned, from a timing plan perspective, Scoot's not making really, really big dramatic changes. It's watching in real time and constantly making small adjustments to optimize traffic flow. There are some situations that are a little bit more predictable, like an event going off, or you just know that there's a certain place, maybe a movie theater or something, where there's going to be a lot of vehicles flooding a certain direction. You can set up a CAST, which is essentially going to more efficiently move people through and change things quickly. So we talk about small cycle length changes and extending a phase timing for up to 4 seconds. Well, CAST is going to say, nope, this is a big group. This is how long they're going to take to get through there. We need to program something a little bit more aggressive in Scoot.
All right, detection, advanced and stop bar detection. Those are as I mentioned, the necessity for adaptive control. And the biggest thing that everybody wants to kind of take away from this is, or at least one thing is that Scoot is agnostic to what kind of detector type we use. So we want to utilize everything that you guys can or have out there on the street today, And then what we'll ultimately try to do is fill the gaps with whatever technology you feel comfortable with, or which is best suited maybe for that application or that need to fill that gap. So that being loops, video, magnetometers, radar, you name it. Essentially, we're able to utilize that those devices out there so that we can put them on the street, and then obviously keep the cost down for implementing the detection for a scoot corridor. So Scoot uses both stop bar and advanced detectors. They both serve a good purpose and a viable purpose. So if we have the ability to have both out there, we want to utilize that. So advanced detection is very important because we actually see cars approaching, and we can make those small adjustments, just like Kai was discussing. We make these small incremental adjustments on the fly as cars are approaching. So we want to make sure that not only we're making those adjustments as they have a green light, but also we can understand what that queue is. So we can understand how many cars are in that pocket or on that phase. Stop bar also allows us to know the extent of the congestion. What is our occupancy levels, things of that nature. So how long people are sitting. So Scoot can make and twist those dials, if you will, and make the proper predictions as cars are entering throughout the corridor. So there, as I mentioned, there's two sides to both those kind of detectors, right? So flow count detectors, being your advanced detectors, are great for demand, right? So we understand how many people are entering, what are queue lengths, things like that, but they're really poor for congestion because there's not somebody sitting on them, or if it is, that queue is obviously really backed up. So, and the idea with Scoot is obviously to minimize the amount of time that queue detectors got an occupancy on it. So it's going to constantly try to adjust and decrease the saturation point. Occupancy, of course, is good for congestion. So we know that people are there, and we know how long they've been present, more or less in each split interval, but they're really bad at knowing how many cars and what the demand is. So a combination of the both really is influential on the Scoot software, and can make real-time, real great decisions out there on the street for you guys. So how it does that, it's Scoot utilize what we call link profile units, and these are ones and zeros that are essentially given to each vehicle. So as the car is approaching and hits that flow or that advanced detector, it is given a link profile. So a sedan, for example, is giving a link profile of 4, but a semi is provided a link profile of 17. So then ultimately we know what kind of cars and what size of cars and how many cars are in that queue. So then Scoot can make those tweaks as it is making and defining what that split interval will be for the future to come. So again, the objectives, of course, utilizing detectors is to calculate, understand the demand at all approaches, right? So the idea is we want to evenly disperse the saturation points at all approaches. Of course, in Scoot, you can define that, you can change that, you can tweak that. You have all the full flexibility and demand on the system, as much as letting it just run free and doing its own thing on the fly as it would. But you definitely can put the constraints on, or you can let it run faster and more wilder. So we're also on the detectors and measuring the queues, big component to understand how much time we need to give on each approach. Then I mentioned, detecting the congestion, how many times, how long people are sitting on those stop bars. And then the biggest thing, too, is reacting to the exit blocking, meaning we don't want to push more cars through if there's not room on the upstream or downstream, however you want to look at intersections. So we really want to understand that too, and that's what Scoot's looking at as a network of intersections under the adaptive system. So some facts, if you guys can read, that's a little small, but as I mentioned, detector-wise, we're agnostic. You guys use what you have out there. We fill in the gaps where appropriate or needed. The detection comes in all flavors, shapes, sizes. Typically we're looking for a 6-foot, as you call it, loop, so that we understand and we can grab that link profile for the vehicles that are coming into the network. You know, depending on placement and what the dynamic is, we'll talk about this, but part of it is a detector survey. But if we're looking at upstream intersections, which we can use those detectors and then also have them come through that closest intersection to make the calls. But typically 30, 40 feet is kind of a rule of thumb there. You know, the entry link detectors can be, you know, 240 feet. They can even actually be closer depending on the dynamic. Some of those dynamic changes would be like driveways to say shopping malls or a gas station, things like that, where we want to make sure that we're capturing the appropriate vehicles as they're approaching the intersection. So we can go to 240, we can go all the way back to 450, even farther back. It really depends on, again, what technology you're using and what makes most sense out there in the intersection. What we can do too, if we have a left turn pocket, the nice thing with Scoot is that how we can remap a lot of the detectors within the system. So even though it's hardwired to one cabinet or the other, we can actually remap in the system so that if your left turn pocket doesn't have enough space for a detector, an advanced detector in that pocket, we can actually use the side stream, as I'm gonna call it, detector to actually understand how many vehicles are coming in and out of that pocket of the left turn. So hopefully that makes sense. And maybe Kai, well, I'll move on and we'll not make it difficult. But that is, we're able, like I mentioned, we're able to move a lot of detectors around so that we can utilize them in various sorts for various informations based on the approach. Let's see. One big thing, detection, right? So is that every fourth of a second, we're actually sending information back to Scoot, and then Scoot is making decisions every second. So those detectors are constantly feeding information in from, it could be 1 to 20 to 30, you know, or even more intersections of detector data entering that system, and it's crunching the numbers and then dispersing that to all those intersections that are out there 24/7, right? And that's that one and zeros. So we're understanding what's hitting, meaning a detector on and a detector off, and then making the appropriate decisions on the demand out there. So detectors can also be used for count or occupancy if we're required. So we get a lot of data from these detectors as well, right? Being a detector-driven technology, you got a lot of information that you can pull from the field there. And then, of course, that can all be exported raw format. They also got nice graphs that can be representative of what's going on there over the course of period that you're looking at.
Talk a little bit about the principles of Scoot on a basic level. To start with, you've got a driver. Your drivers are going down the street. They're hitting the detectors that are seeing them, both on advanced and stop bar, like Zach said. The system is then compiling all of that information. So one of the important things is it's processing that information every 10th of a second. So you've got a lot of data going on throughout the day to create what's called cyclic flow profiles. So in order for you to make a noticeable difference in the system has to be constantly fed the current information for how many vehicles are out there. We want a profile of what does this particular intersection do. It's not like one intersection has the same kind of flow profiles as the next one. So at every single location where there's detection as part of the Scoot network, it's constantly creating a cyclic flow profile so it can make the optimal adjustments. Then put into a traffic model. So as Zach mentioned, the traffic model is overlaid on your existing system. The cool thing is this isn't something that's going in and choosing traffic plans or anything like that. There's the general model, which is the intersections you have out there. It's supplemented by the cyclic flow profiles that are generated by the detectors. And then we can take that information and optimize it. We can say, okay, here's our baseline, which is your existing system. These are all the variables at each of the intersections. And then we're going to make small adjustments to the cycle, offsets, and splits. After we've taken all of that into account, you know, on a global level for all of your intersections that are part of this, then they're going to make a decision, send that decision to the controller, and then you've got the information pushed out in the field. So having an optimizer for each of those three items, the split, the cycle, the offset, and the split, is what makes Scoot kind of unique. You can have other systems that are able to handle maybe one of the three of those, two out of the three, but to put them all together, that's what you really need for a truly adaptive system. It's not just doing after the fact reactions to traffic flows. Queue modeling. So essentially what Scoot's doing, and I try and explain this in a way that kind of makes sense to me, which is the goal to move traffic efficiently is to reduce your arrivals on red. You want to increase the odds that your vehicles or your platoons are arriving on green at each intersection as often as possible. Anytime anybody's arriving on red, that's when you're getting your complaints from your citizens. That's what's really slowing down traffic. So the idea is, look all the way upstream at this entire system. The system is looking at the entire queue and it's saying, what can I do to maximize the size of that queue that's arriving on green? Of course, you can't move everybody every direction on green. That'd create a dangerous situation. But Scoot is going to try its best to, if you can picture this queue model, find the very tip. They actually call this the tip of the seal. The goal is to say, okay, here's as many people as we can squeeze into this platoon, and we're going to make sure that that large group is moved safely through the intersection as often as possible in as large as amount as possible. So if the split, which is the gray area, can be reduced, that's when we see a reduction in stops, delays, and essentially congestion. One of the things with Scoot, we always want to talk about travel time. How long is it going to get me from point A to point B? Well, an equally important metric, and perhaps a metric that we're able to control even better in Scoot, is how many people were moved through the intersection. Have we changed throughput? Maybe you've only reduced the actual travel time by a couple minutes or whatever it is, which is actually a large period of time in a lot of cases if you add it up over an entire year. But the idea is, no, we've moved this many more people through, and we've reduced rush hour at the margins on either end. We've shortened the period of time where traffic is really, really bad.
So yeah, one of the use cases here is also transit signal priority. I think in a lot of agencies, they have a bus of some sort going through, being a metro or a locally city-owned bus system. And out of the box, Scoot comes with the availability to integrate transit signal priority. So as some of your intersections today, what it's going to do is be able to provide the phase reductions and extensions and things like that with the technology that maybe you have out there, being Opticom or another form. But the nice thing too is that Scoot's going to look at that transit signal priority essentially from where the transit is, and then to its destination. It's going to look it throughout the network so that we can really help and push through those vehicles on a timely manner so that they are arriving on schedule and not getting delayed too much at the intersection. Some other more advanced capabilities is using AVL, so active vehicle location. So then we can actually take that technology in to Scoot so that it can make better, wiser decisions based on maybe the occupancy of the bus, if it's behind or ahead of schedule. And then that way we can make decisions on the street so that those buses are getting through efficiently at each intersection. So the system architecture of Scoot, it's actually quite simple. So we have a Scoot server. Scoot can actually run independently from any central system. So we can communicate via that server platform down to the local controller, which that local controller then is feeding us all that detector data through the communications network that you guys have in place. One thing to note, on the network for communications, we can use all kinds of forms of that as well. We have systems out there that are running on Ethernet over copper. We have wireless installations. We have fiber installations. So we, again, try to utilize what you guys have out there as far as the network infrastructure so that we decrease the cost on that end, and we can put the money forward on the power of Scoot. Then, of course, if you guys have a central system, that can be attached. So if there's any minor changes that you need to make at the controller level, you would have that capability as well. So, we could utilize our tactics if that's the system that you have. But as I said, Scoot can run independently of any system that you have if need be.
So the Gemini box, Scoot is controller, like Zach said, central system agnostic. So it doesn't matter if you're using Siemens controllers. Now, there's the advantage of if you are using Scoot, then any of the additional hardware required would just be back at your IT department. Everything else can be done just with your regular M60, which is the current version of the CPAC Siemens controller. But it doesn't make too much of a difference to us if you guys have a different system. There's lots of other controller manufacturers out there. It's important for Siemens that they work across all platforms. So this is a picture of the actual third-party device. This is, I believe, 1 generation ago. So it's even smaller than it is now. So just put it up there and near your detector rack, add it in. It's compatible with the 330X style, which is kind of like what our WashDOT and WashDOT managed agencies use in Washington State. NEMA TS1, TS2, Types 1 and 2. It can handle any detection technology, Ethernet based. The communications, high latency tolerance, and it's also got a web-based interface. So a lot of the other systems that you'll see out there are going to require a lot of additional hardware. There's not too many controller manufacturers that have their own adaptive system. It's oftentimes a truly third party. We've got a number of installs. City of Seattle, Renton, they're both using Scoot on Siemens systems, and they don't have any additional hardware out in the field. So, but even if you do, it's not a problem, and Scoot will operate the same way. So Scoot implementation, it's a pretty simple process. It can be done streamlined for as quickly as you guys might need it done, but essentially what we have to start with is a detector survey out in the field. So, this is a service that us, in conjunction with Siemens, we go out there and figure out, what the detection lay of the land is and where upgrades might be required. We really can't emphasize enough the importance of detection. All of the calculations that's happening in the Scoot system are based on reliable detection. So it's an overused term, but garbage in, garbage out. Your system is only as good as the quality of the detection. So the reality of it is, in most agencies, this is a big piece of the puzzle, and we get it out of the way right at first. We're willing to work with any agency and say, okay, this detection looks fine here. Let's move this over here. So we have like manufacturers and like brands. This one requires advanced. This is a short approach. So let's turn this camera around here because you can reuse it. So in a lot of our installs, it really has been a mishmash of detectors, but the important part out there is knowing that it works well and is reliable. Controller upgrades, using Scoot's been around forever, so it works in a lot of controllers, but let's go in there and make sure your controllers are all in good shape, speaking the same software, reliable, got the latest updates, things like that. Detector installation, so inevitably, like I said, there's going to be some upgrades and new detection that's required unless you have a perfectly operating system that's already got advanced detection everywhere you need it. We work closely with your guys' IT department to do server installation. If anybody's interested after this, we can share kind of the server requirements. Network communications. Now, I'll talk about this in the next slide. It's not you don't go into Flash or shut off the whole system if you lose communications, but having reliable communications, no matter what kind it is, wireless, fiber, Ethernet over copper, we want to make sure that's all up to snuff and all of the intersections are connected and talking at efficient data speeds and as reliable as we need it. Data entry, so moving over your databases, entering all that information, that's stuff that any one of our 5 technicians will be helping you with. Validation, going through and making sure that all the information is correct, getting it ready kind of for fine tuning. So fine tuning, letting the system kind of work in the background. Kind of do this before we turn the entire system off, but Scoot gives you the ability to see what changes it would be making, would it be running. So this is the time for making sure that the changes that are being made are subtle enough to not create any issues, but also aggressive enough to be ultimately making a positive difference. And then going live, of course. Real-time adaptive. So we talked about cycle lengths. The minimums and the maximums, they're defined by the users. So a lot of systems will call themselves adaptive, but they'll be confined by the number of optional patterns that you have within your system. So maybe you've got 30 patterns, and their system's going to choose one of those that it thinks is most optimal for the situation. It's limited by, I mentioned, the number of actual patterns you have, and oftentimes it takes an entire cycle to catch up. There are no plans in Scoot, so it makes changes to the cycle time anywhere up to 240 seconds. It's reacting as needed and not saying, oh, this one's close enough, this will suit their needs. If you do lose communications, the controller is going to revert back to your local time-based coordination. So you set up your time base, and you've got peace of mind that if something happens with the system, you lose comms, then you're not going to be just running in recall. It's going to go back to your time-based coordination. Same thing with the detector failures. It doesn't create some awful situation. It's just going to use the historical data that's in the controller. Phase sequence, you configure that right at the controller level. Optional phases served on demand. Maybe at some time of day you want to run a second left turn phase or something like that. Other times of the day you want that to be a through movement. There's a lot of flexibility in changing when these plans are called up, depending on the particular need. Again, the whole idea of Scoot is there's not one size, one time of day, one time of year even that fits all. We want to be able to react real time to both expected and unexpected changes in situations. Scoot is it's a highly active system that's constantly making changes, and it can run 24/7. But the reality of it is some agencies say, you know what, it's just not necessary. We don't have the volumes at 2 a.m., so we're just going to revert back to our local timing plan at certain times. So it's a selective timetable that gives you the option to turn it on or off. It's an operator timetable. Scoot gives you a lot of flexibility. What a lot of people want to see in an adaptive system is a system that they can set and forget. Well, we've got that option as long as we've done a good enough job fine-tuning it on the front end. Scoot allows you to be just as active or as inactive as you'd like. Some people have turned it on and we just about never hear from them, while other agencies, they've got a person or a dozen people who are committed just to watching Scoot and making changes because that's the level of hands-on their agency wishes to have with the system. So a lot of flexibility there. Fine-tuning, route priorities by time of day, setting up your split weighting and your offset biasing. So maybe you've watched the models while we're in the fine-tuning phase and said, this is great, we're moving traffic through here, but we've created a gating situation or a situation that could be alleviated by gating. Well, maybe we want to increase the offsets here. Just doing those small things to fine-tune them before we go live. For those of you technicians on the line or people who have opened the traffic signal cabinet, one thing they're not making a whole lot more of in these things is room. And what most people want is to be able to add an adaptive system without pouring a new foundation, changing your cabinet spec. Western systems, both with Scoot, but also some of the other cool things we're doing with cabinets, we realize that there's only going to be an increase in your IP addressable devices in the cabinet. This is an agency, a local agency that's using an adaptive system, and they've used, you can see on the second shelf there, that's the third-party device. That's all related to the adaptive system. Kind of hijacked the real estate in their cabinet. You can actually see, based on the number of load switches, that it's not a particularly complex intersection, but strictly the hardware of this third-party provider is taking up a lot of space in the cabinet. This particular agency might want to add another shelf to accommodate some space. I can see a rugged comm switch there on the top of the detector rack, but another thing that you can do is add a system that doesn't require all of this additional hardware. So that's what we got.
Right,
we welcome you guys.
Yeah.
All right, thanks.
Thank you, Kai. Yeah. One thing I just want to state, adaptive, as Kai alluded to, is expanding quite a bit, and it's expanded quite a bit. Luckily for Western systems along the West Coast, we have about 200 plus intersections along the West Coast, from Washington down through California. So the expansion of Adaptive is really taken over. Our installers have become very proficient and can really walk you through, hold your hand through the process. So as far as Adaptive, we've got the process down really well and can make your life a lot easier when thinking or wanting to install. Of course, my team and the team of individuals can give you and provide you more information as you guys gain some interest, or maybe come into some funding, or maybe some powers to be are really wanting to look at integrating this into your network of intersections. So, of course, the Adaptive or Scoot Adaptive does not have to be a particular size or number of intersections. A lot of agencies typically will start small and then expound off that. So we're open to, the 2 to 3 intersections all the way up to, we've done 50 plus. So the shape and size is really dependent on what you guys have available, what you guys can take on. But needless to say, Western Systems and the Siemens team is, again, very proficient and can help you through that process. With that said, I hope you guys enjoyed. If there's any takeaways, or any questions following this, or questions now, please feel free to ask.
Great. Thanks, Kai and Zach. We'll go ahead and get started on the Q&A process. If you have any questions, now's the time to go ahead and use your chat feature within the GoToWebinar toolbar. And looks like we have a couple coming in here. First one is, how is Scoot different from, say, an InSync or Synchro green adaptive system?
I can take that one.
You want to take that one?
You know what? Yeah, sure. There's a couple differences. We'll start with the hardware side. I showed you a picture. I believe that's an InSync system in there, and InSync's interesting. I don't necessarily want to pick on just them, but the entire system is kind of marketed as a set and forget. But what we find with most of our agencies is they want to be a little bit more active in their traffic control program. So InSync requires you to use, or at least makes it very difficult to not use, their detection. So you've got your city spec, and they say, nope, we've got our proprietary cameras that we like out here, and that's what you guys are going to have to use. In addition, because it essentially hijacks your system, you got a lot of cabinet hardware in there, so that's a lot to jam in there. Adaptive systems should be able to seamlessly integrate with any style cabinet, be it Caltrans style, TS1, TS2. The particular cabinet we showed you guys was a TS1 cabinet with a lot of wiring going on. You've still got your A, B, C, and D connectors, a lot of wires flying all over the place. That's okay. That's okay for Scoot. You want to focus on moving traffic more efficiently, not necessarily upgrading cabinets if there's nothing wrong with them. That little Gemini box is going to fit right up there near your detector rack, and that's it. And as we mentioned in the presentation, we don't require a certain manufacturer of detection, just require that it's reliable. From a software standpoint, I think I touched on the mode of operation is that Scoot is changing in real time. It says we're not able to come up with the right pattern. We want to have control of the splits, the cycles, and the offsets, and make changes to every single one of those to optimally flow traffic. If they were confined to a pattern, it just wouldn't work quite as efficiently. And I think the proof is in the numbers with that. When you look at before and after studies, Scoot systems are proven to increase travel time reliability, reduce emissions, and move more traffic through the intersections. And that's because it's got greater control of kind of those variables.
Great, thanks, Kai. We got another one just came in here. What are the hardware requirements for Scoot?
I'll take that one, Kai. Yeah, so the hardware requirements are kind of dependent on what you guys have out there, but actually relatively simple. Everybody's got a controller out there in the field. It, depending on the manufacturer, can really depend on the seamlessness of the installed Scoot. So if you have a Siemens brand controller, then we'll utilize that, and the Scoot system will just plug into the Ethernet port of that. If you have a third-party controller, and you want to stick with that controller type, that's perfectly fine. That's when we would introduce the Gemini box and be able to integrate Scoot with that manufacturer's controller. As far as the network, again, we want to try to utilize the network. The biggest thing, of course, is the reliability of that network, but we can utilize any switch type as long as it's got the proper communications and the bandwidth to it. So we'll utilize, again, the copper if that's in the ground, the fiber if it's in the ground, or wireless communications if that's the best option for you. Then, of course, the detection, right? So the detection being a critical part of that. So we try to utilize any loops or video cameras or anything like that you'd have out there. But if we needed to add some detection, we'd, utilize what you're comfortable with, but also cost effective, right? And we're maybe best suited for that application. That could be, a couple different source types of detection. We've had a lot of success with video cameras and the hybrid that we supply with the video and radar system because of the flexibility of the detection and being able to properly place it or make the adjustments on the fly. So that's one of the things that we talk and walk you guys through when looking over you guys' full network of intersections, just to understand the lay of land. And then we start the process there about procuring or getting whatever is needed for the hardware to implement Scoot.
Great, thanks. That looks like all the questions we got today. So we appreciate everyone for attending the webinar. Thank you, Zach. Thank you, Kai. And everyone have a great afternoon.
Thank you, everyone.